Let's do it. Good evening, everybody. AP Stats Cram crew. I'm super excited to get started today. As you can see, we are finally to the point in the semester or in the cram season where we can start talking about null hypothesis. Do we reject or do we fail to reject? I've got my little Bitmoji right up there to talk about that. Also up there, you can see the next things coming up. We've been on kind of a Tuesday schedule for the past few weeks. We are going to be swapping to some weekend schedules coming up soon. So you can see the next cram is on Sunday at 1 p.m. Eastern Time. And the Unit 6 trivia is tomorrow night at 9:30 Eastern Time. All right, and today we again are going to be looking at hypothesis tests, and particularly for categorical data, in other words, proportions. Okay. All right, so this stream, as always, is being recorded. And, you know, names in the chat, that sort of thing. We've been through this a few weeks. Just make sure if there's any reason why you don't want your name featured in a replay to use just a first name, something like that. All right, catch Fiveable on the socials. Twitter, Instagram, YouTube. I believe we're also on TikTok, which is my favorite time waster right now. I've learned a lot of cool things too, though. All right, so coming soon, again, next week's stream, swapping to Sunday when we continue looking at inference for Unit 7, which is inference for means, and our trivia tomorrow night. Great opportunity to look at some multiple choice questions and just some big topic ideas. And then our 5-hour cram finale, definitely bookmark that time to make sure that you are good to go. I am super pumped for that. I'm already kind of in my mind going through all the things that we need to tackle that day in terms of how we're going to structure that. But I'm super excited to get going with that and knock that out of the park the day before the exam. I hope you are like me and you are so ready for May 17th just to go into that exam and just hit a home run, knock it out of the park, and then move on into summer. It's probably your last AP exam. There's not many AP exams after AP Stats, so I am so ready for you guys to go and knock that out of the park and have some rest after such a crazy school year we've had. Such a crazy school year. So in this stream, since it is the first time we've looked at hypotheses test, we're going to kind of talk about what that is and what that's going to look like. We're going to look at the different parts of a hypothesis test. How do we write the hypotheses? What are the conditions for inference, in particular for categorical data? Calculations, how do we calculate the test, and then how do we conclude the test? What do our calculations mean? What does that tell us? We're also going to look at type 1 and 2 errors. That's a little side part to hypothesis test that you definitely need to know. And then we're going to look at an example from the last full-length AP exam that was in 2019. There's some good things to talk about that pop up in that problem that I think will be beneficial for us to work through together as a team. I see Sanders already in the chat. Use the chat, use the Q&A session, the Q&A option as we are as we're working. I just enabled the Q&A, and Sanders an awesome TA. He will answer your questions if I don't catch it, and we can help you to make sure that you are prepared to do a hypothesis test for categorical data. That is our goal for today. So the first thing is, what exactly is a hypothesis test? What does that mean? How are we going to go about completing that hypothesis test? It is the testing part of inference, okay? So remember last week, we started with confidence intervals. Of course, we had technology issues out the wazoo. The last stream was a bit of a nightmare, but we did get through most of it before we had issues. And we talked about the a confidence interval is used to make a prediction about a population. So a hypothesis test, we are going to be given a value about our population. So we're going to be given something that we're comparing our sample to. And we're going to see, is our sample matching what someone is saying about the population, or is it so far off that what they're saying about the population is wrong? That's ultimately our goal. We're testing someone else's claim about the population. So keep that in mind as we work through things today. Two types of inference: prediction, which is a confidence interval, and then a test comparing that sample to some claim about the population, which is where a hypothesis test comes in. Again, it is usually necessary when we have a claim about a population and we want to test that the claim that matches that random sample that we've collected. So when we're dealing with proportions, we are going to run a z-test. Okay, we'll talk next week about t-intervals and t-tests that come up with means, but when we have proportions, let me go back and say this. When we're dealing with either one or two proportions, not three or more and not multivariable proportions, we are going to use a z-test. There is the little caveat of chi-squared testing, which comes up when we have more than one variable, or maybe when we have multiple categories. But if we're only dealing with one variable and at the most two categories, then we are going to look at doing a z-test. A z-test is kind of our go-to. And you'll be able to tell the difference. Once we do chi-squared in a few weeks, it's a pretty clear difference between the two. All right, now this picture right here really sums up what we're doing. Okay, so just like with confidence intervals, we are going to take our data and match it to a normal curve. And if our sample, okay, so the middle of our normal curve, that's our mean, is going to be whatever the population claim is. Okay, so that is our mean. You know, the article says that 20% of people grow their own garden. Okay, and anything that is within that fail to reject region, okay, we'll call it that. Anything that's within that region doesn't give us any evidence against whatever the author was saying. It doesn't give us any evidence against the 20% of people plant their own garden. Okay. Now, if our sample falls somewhere in these two tails, then that is where we can get evidence that that claim is probably not right. Okay, based on certain significance levels. So we're basically looking at where does our sample fall on the normal curve if the middle of our normal curve is the population proportion that we're given based off of an author's claim, based off of an article maybe. Maybe we're comparing it to a previous time. That'll come up in today's example. We're looking at 2017. Did things change from 2017 to 2018? Okay. So yeah, that's kind of that. This picture kind of shows a graphical representation of what we're doing. We're trying to see where does our sample fall at. Does it fall in an area, one of the two tails, that leads us to reject our null hypothesis, or does it lead us to fail to reject? So the different parts of a hypothesis test. The key words or phrases that you're going to look for. If you see one of these two, which you probably will on the AP exam, it seems to be number 4 on the free response. That's the way it was, I know, in 2019, which is the number we're going to look at from 2019. And it also has showed up quite a bit. It's usually number 4 or 5. It's usually an inference question. And if you see that one of these two phrases, is there convincing or significant evidence of blah, 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 or do the data give convincing or significant evidence of blah, 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 blah. Okay, that should cue you, hey, I'm doing a hypothesis test here. Maybe it's about a proportion and I'm doing a z-test, Maybe it's about a mean and I'm doing a t-test. Maybe it's about two categorical variables and I'm doing a chi-squared test. But as one of those options, okay? Probably not a linear regression t-test. That's not very common. Maybe in the investigative task. All right, so just like we did with confidence intervals, I like to follow the same acronym, okay? So we're going to state, which involves stating our hypotheses. What exactly is it that we're testing? Put that into, word form or equation form. And also identify those parameters of interest. So in this case, we're looking at proportions. So I want to do P equals the true proportion of, or difference of proportions of whatever variable it is that I'm looking at. Okay. I need to plan. All right, so I need to do my conditions for inference. Over there in the chat, let me know what are the 3 conditions for inference that we talked about last week with confidence intervals that are going to be the same thing today. What are those 3 conditions? Yes, random is one of them. That is the first one. And the other 2 is normal and independent. So now that 10% condition is the independence condition. Either one of those 2 are generally accepted on the rubric as listing those out. All right, so your conditions, which we'll come back and we'll go in that more in depth. But yes, it is random, normal, and independent. So once you have stated those conditions, and remember we talked about this with confidence intervals, that formula for a confidence interval has 3 parts, and each of those conditions matches one of those 3 parts. Okay, it's almost like the proof for how you know that formula works. Okay, if I'm using quadratic formula, I have to have a quadratic equation. I can't just use the quadratic formula on a linear or a third degree a cubic function, okay? I have to use it on a quadratic function. So there has to be some sort of condition met for that formula to work. And that's the same thing here. We have to have 3 conditions in order to use that confidence interval formula, which is tied in with our hypothesis test a lot. And you'll see that as we sort of work. You might have seen that with that last graphic we saw. So once you've proven your conditions, then you can do your calculations. All right, your calculator is the absolute best thing that we could do here. Okay, that is just like super awesome. It makes your work so much easier, but we do need to make sure we include, so you don't seem like you're using in the answer, but it does give you a definite reason why you should do that. All right, and then the last thing is to conclude. And the big part about your conclusion for hypothesis test is that you're comparing your p-value to your significance level. So is your p less than, generally, what significance level do we typically use? You can throw that into the chat. If we're not given a significance level, what do we kind of understand that we would use here? Yes, 0.05. I'm seeing them rolling in now. Yes, so 5%. And a lot of times they sneak those questions in there. It's not really a hypothesis test question, but you do some sort of probability, and then it says, does your answer in A lead you to think that this is likely to happen, or is this likely to be the truth? And if the answer is less than 5%, then that leads you to doubt that particular claim. Okay, if something happens and the probability of it happening randomly is less than 5%, then that's where you kind of doubt that claim, because you're comparing it to 0.05. You're comparing the p-value to a significance level, even if it's not so obvious like the keywords and phrases I have at the top of the slides now. Yes, occasionally you do 0.1. That would be like, so 0.10 is like a 90% confidence interval, which again occasionally shows up. And then 0.01 is like a 99% confidence interval. So there are times where they ask that. There was also one a few years ago that asked for a 96% confidence interval, which would be a significance level of 0.04. You can see those complements play into each other, especially with the two-tailed tests that we get to in just a minute. Okay. All right, so the first thing we're going to look at is stating our parameter of interest. Okay, you have to make sure that this is clear for the reader what it is you're looking at. So in this case, since we're looking at categorical data, we are looking at either one or two proportions. All right, so in this case, you're either defining your P or defining your row. I know some people have said they use pi as well. Whatever it is that you have been taught to use and you've been conditioned to use for your population proportion, do that. We are not talking about p hat here. P hat is our sample proportion. That's a big difference to differentiate between there. But our P with no hat, all right, like me right now, no hat, is the population proportion. I know sometimes I wear a hat. All right, so if you are doing a two proportion test, be sure to identify both of those proportions and also use meaningful subscripts. All right, what is the big C word here in AP Stats that just about every single question has to have on it all the time? You can throw that big keyword in the chat. I've stressed it so much, and I know that you guys are probably tired of hearing me say it, but you have to get it down before May 17th. What is that big C word we have to include here? Sometimes it's included with cuss. It's one of the things whenever you are cussing the data that you have to include. But it's not center. Center is where what comes from with cuss. Keyword there, not conclusion. Context, yes. Okay, I was just typing it and putting it in the chat. Context, context, context. No bare numbers. Make sure that whatever number you're using, it is tied to a particular concept. Okay, context, context, context. Make sure, whatever your proportion is. Don't just say P1. All right, if you're looking at the difference between the red team and the blue team, do P red, the true proportion of players on the red team who won their match. Okay, and then P blue is the true proportion of players from the blue team who won their match. Okay, well, you know, whatever Quidditch, whatever game we're talking about there. I love how Google Captions actually did translate Quidditch correctly. Anyways. Maybe we need a Harry Potter question next week. I'm thinking next slides is going to have a Harry Potter question on there. So be on the lookout if you're a Harry Potter fan. All right, so the first part of stating that SPDC process is to state what is P. What is it we're looking at? The true proportion of whatever. And then the next thing is to state our two hypotheses. We have a null hypothesis and an alternate hypothesis. Okay? And here's a little graphic that kind of shows you what the null hypothesis is. Basically, the null hypothesis is the idea that there is no connection, there's nothing weird going on, there's no wow factor, everything is business as expected, it's no surprises. So the examples here is it says cats show no preference for food based on shape. Basically, they eat it if it tastes good. It has nothing to do with what shape it is, which we know cats are a little bit strange creatures, okay? I got Grumpy Cat up there with me. We've been fostering some dogs. They actually just left right before we hopped on here, and my cats have been really upset with us and having 2 dogs in our backyard. They've not been able to have free roam as much. So they'll be happy now that the dogs are gone. They have been grumpy catting it around the past few days. Plant growth is not affected by light color. So again, there's no strange correlation there. Everything is business as usual. Okay, yellow light, pink light, it doesn't matter. They grow the same way. And then the other one is age has no effect on musical ability. You know, same age, I would be willing to bet that would probably be rejected. Well, I don't know, it depends, I guess. It depends on your experience. I feel like that one you could have a lot of bias introduced into some samples there. But, so yeah, the null is that it's business as usual. If the article claims that 20% of people grow a garden, then your sample is pretty much going to reflect that. Your null is that it's 20%. It matches the article. There's nothing weird here. Everything is business as usual. We're going to keep going on, believing the thoughts we've had, nothing new. Okay, that is what the null hypothesis is. Okay, and then the alternate hypothesis is the claim that your null is not correct. Okay, that maybe there is something going on that's different than our null hypothesis. And we have some different options of writing that. Sometimes it's just a statement that there is a correlation or there is an association between two things. When we get to chi-squared in about 2 or 3 weeks, that's sort of what it is. Okay, the alternate hypothesis is that, hey, these two variables are correlated. But most of the time, it's simply that the population parameter is not whatever that claim was in the original problem. It's, you know, something's a little bit off. Okay, maybe it's less than, maybe it's greater than. Those would both be examples of one-tailed tests because your samples only has to fall in one end of the normal curve, one end or the other. And then you have a two-tailed test, which is where it's not equal to. So you're not really saying that it's less than what the population claim says or greater than. You're just saying, hey, that population claim is not right. Something is wrong there. All right, so here is an example of what this sort of looks like. If you were doing a one prop z-test, all right, your null hypothesis is that P equals whatever the claim value is from the problem. Remember, you've already stated P equals true proportion of people who grow gardens. So then your null hypothesis is that P equals 0.2. Don't use percentages. I feel like that just throws you off when you start working in the calculator. There's not a percentage button on the TI-84, so that can just really kind of throw things off. And then your alternate hypothesis is that P is either greater than, less than, or not equal to some form of non-equality, whatever that claim value was. So in the example I've been using, 20%. P may be greater than 20%, if that's what the question is asking. Do the data give convincing evidence that the true proportion of people who grow gardens is greater than 20%? That would be P greater than 0.2. If it said just not equal to 20%, you would put, you know, the equal sign with a line through it. It just depends on the way the question is broken out. Okay, and so that's if you have one proportion. So you have one sample, you're comparing it to one population claim. All right. And then if you have a two-prop z-test where you have two samples, on that one you're generally comparing, are they equal to each other? Okay, so is the proportion of people who grow gardens in their 20s equal to the proportion of people who grow gardens in their 50s? All right, are those two proportions equal to each other? Okay, and then again, if the statement in the problem is that do the data give convincing evidence that people in their 50s are more likely to grow a garden than someone in their 20s? Then it would be the proportion of people in the 50s, P sub 50, greater than P sub 20, okay? Or whatever type of information you like to choose for that. Okay? So one prop z test, you're just equal to a number, and then either greater than, less than, or not equal to a number. Make sure, and this is important, it shows up on multiple choice questions. A little test taking tip. Never underline your greater than or less than sign. All right, it would make no sense to be testing the claim that P equals 20% by testing it against that P is greater than or equal to 20%, because literally the both things are saying almost the same thing, or at least there's some overlap between the two, and there needs to be a clear defined difference between the ho and the ha. And if you say greater than or equal to 0.2, there's no clear defined difference. They could be the same. So you have to say that it's greater than 0.2. Don't underline your inequality sign in the alternate hypothesis. That shows up a lot on multiple choice where you're picking out the right hypothesis. If you see one with a greater than or equal to, mark it out. It's not it. Okay. All right, now our conditions for inference. We already talked about those. Okay, the first one is random. So one of two options. Either the sample or samples have to come from a random sample, or if you're dealing with experiments, the treatments should be randomly assigned. Little review back from a few weeks ago. Okay, if treatments are randomly assigned, what do we call that as a study? If treatments are randomly assigned, what do we call that as a study? Yes, Sander, I like that answer there. Proportions are for proportions and samples are for means. Great answer. So what kind of study is it if treatments are randomly assigned? I'll give you a little hint. The answer is actually there. I just wanted to rewind a little bit. Complete random design, not necessarily always. That's not the word I'm particularly looking for. I'm looking for a word a little bit simpler than that, actually. Okay, so we have random assignment, but what kind of study does that make it? Okay, we have two types of studies we looked at when we looked at Unit 3. And if the treatments are randomly assigned, which of those two studies is it? Yes! Okay, it is an experiment. It was actually here. But I did want to get you back thinking about that again because that's such an important concept. So if treatments are randomly assigned, that means that it is an experiment. Okay, if treatments are not randomly assigned, there's no interference with the participants between the researcher and the participants. That means it's an observational study. Now remember, an experiment, you can establish causation. So you can say X causes Y. With an observational study, you can just say X is correlated with Y, which is not near as strong of a statement because you didn't randomly assign people to group A or group B, all right, between the two variables. All right, so random is our first check, and in order to prove that, For the reader, you just want to quote the problem. An SRS of 80 families in their 20s. An SRS, a simple random sample, or just a random sample of 100 families in their 50s, whatever it's from the problem. Just quote the problem, straight up plagiarize it, whatever, and that gives you the points that you'll need for that. The next condition is independent. I see that over there in the chat, and the way that we check that is that our population must be at least 10 times the sample size. Okay, so we have to make sure that our population is at least 10 times our sample. So it's reasonable to believe that our population is at least 800. It's reasonable to believe there's at least, 80, so 800 families in their 20s. Okay, which is obviously true. That's a very reasonable statement to believe. Now, independence is not necessary for experiments. So if you are looking at a problem that is a very clear experimental design because it has randomly assigned, for independence you could state not necessary because it's an experiment. If I were reading that, I would be like, yes, you got it, that's good. Even though I don't know that would necessarily give you points, you could just skip it altogether. I like putting random, independent, normal always, anyways, and then for independence, if it is an experiment, just make a note that not necessary because it's an experiment. That way you keep that same structure of random, independent, normal. And normal. All right, so our large counts condition. So NP is at least 10, and N1 minus P is at least 10. We talked about that last week. Basically 10 expected successes and expected failures. We want to base this off of the population proportion given in our null hypothesis. With confidence intervals, we used our p hat here. We used n times p hat and n times 1 minus p hat. The reason why we did that is because we did not have a population proportion. So we used the next best thing, which was our sample proportion. With a hypothesis test, since you have a null hypothesis, you have some value to use for p. All right? So you are going to use that null hypothesis to multiply by your sample size. Okay? Be sure to use the null p, not the sample p. When you are doing a two-prop z-test, you want to verify that all conditions are met for both samples. Another little caveat here, and this is something that I've been working on since the CED came out last year and adjusting my thinking on it. When you have two proportions, that condition check for normal, and this might be kind of new to some of you, you have to pool your data together. I'm going to pull up the reference page and show you this, okay? So this is the reference page that you get when you do the AP exam, okay? They got some formulas here, some of which are just kind of cumbersome. The mean formula, you add them up, divide by n. They got to put fancy math stuff here to confuse you. But whenever you scroll down here, okay, if you're looking at two populations, P1 and P2, when you assume that the two populations are equal to each other, that there's no difference between the likelihood of making a garden in your 50s versus your 20s, your standard deviation formula changes a little bit, okay? Last week with confidence intervals, this is what we used, okay? Now, since we are pooling our data together, this is what we are going to use, okay? So you're going to take your p hat combined from your sample, which is the formula down here, times 1 minus p hat combined, that's the complement, and then times 1 over our first sample plus 1 over our second sample. All right, now to find that p combined, so the p over here that we're using for our condition for normal, standard deviation comes up again later, and we'll get there with the calculating part. But so that NP, you have to find the combined p-value. One of those small little caveats that you have to do. You always pool proportions. You do not pool means. The only time the calculator is going to ask is for means, and you don't pool. So if you're in the calculator, just think don't pool, okay? But with the normal condition, you do have to pool, combine your two sample proportions to create your one p-hat combined. All right, so you would add up your two numbers of successes and divide it by your total two samples. And then you're going to use that times your first sample size. You're going to use the complement of that times your first sample size, and then the same thing for both of the two samples. Okay, so weird little caveat there. You pool proportions, you don't pool means. And we will we'll definitely touch on that as we work through things. All right, so those are your conditions: random, independent, normal. All right, kind of the standard get up there. We've been doing that for 1 week now. We're going to do it a lot more next week. I forgot to take away these animations. Boo. All right, so then the next thing is to do the test, to actually calculate the test. And I'll pull up my calculator here in just a second and show you what that looks like. So it is a one prop Z test. Again, if you're doing proportions, it's always Z, unless if it's one of the weird proportions with multiple categories or with multiple variables. In that case, it is a chi-squared. A one prop, two prop Z test. You're never going to run a Z test without prop in front of it. And we mentioned that in the chat earlier. It is so confusing. And we'll talk about that next week. We will. I'll mention why that's there, but you're never going to use it. Okay. It's silly that it's even in there. I've looked at going into my students' calculators and removing the tests that we don't use. I don't really know how to do that on the TI-84. I also don't know if that is altering the calculator, that sort of thing, and I definitely don't want to walk that line and, you know, possibly break one of AP's rules or anything like that. So it's best just to know that if you're doing a if you're doing proportions, it's going to have prop in front of it, like Sandra mentioned earlier, and it's going to be a Z test or a Z interval, depending on how many proportions there are. All right, so be sure to include the p-value and your z-score in your response. So the p-value, okay, I hope I have a picture here. If not, I can go back to one. It is the p-value is the probability of obtaining whatever sample proportion we had under the assumption that the null proportion is the accurate number for our population. Okay, so yeah, I do have a picture. All right, so right here we have our p-value, we have our z-score, it gives us everything we want. So I created this, and look at there, 20%, that's exactly what I was saying. So let's say that an article says that there is 20% of people in their 20s have a garden. So that is going to be the middle of my normal curve, okay? And then I pull out a sample of 100 people in which 11 have a garden, 11 out of 100 people. All right, so that's 11%. So 11% falls right here on my normal curve. Okay, let's go back to the that reference page. Okay, so remember we are going to calculate that standard deviation right here. So our p-hat was 11 times, or no, over here, I'm sorry. Our p-hat is 20% times 80% divided by 100. That gives me my standard deviation. Okay, so then if that gives me my standard deviation. Now remember, a normal curve goes 3 standard deviations out and 3 standard deviations out. And it's going to fall right here. Okay, 0.2 times 0.8 divided by 100 and then square root it. Okay, that gives me the standard deviation of my normal curve. Okay, so I have a mean, which is 0.2. That's what the article claimed. And then I have a standard deviation based off of that formula, which tells me where it's at. So then I can look at where does my sample fit, okay? My sample of 11% is going to fit right here, okay? So the p-value then is the probability of getting 11% in a sample of 100 or less, given that, you always need to include that, given that the null is true, given that it is centered at 20%, okay? You'll have a multiple choice question on the AP exam that will ask that. What is an interpretation of the p-value, which is different than concluding based off of a p-value, okay? And it's given that the null value is true, what is the probability of getting a sample of 11% or less, or it may say getting a z-score of negative 2.25 or less, okay? That's the probability. So that p-value is actually using a normal CDF to calculate things for you. Just the one prop z-test does it for you, okay? You don't have to worry about doing all that. Okay, and then our conclusion, this is the part where I have up here in my Bitmoji that you're used to thinking. So our p-value is where the money's at. That's where we're really going to break things down. If our p is low, we reject or drop our hoe. All right, I hate using that terminology, but it's what we always remember. The p is low, you drop the hoe. So if the p is lower than our significance level, which is typically 0.05, we reject our null hypothesis. That is evidence against that null hypothesis because it's such an extreme example. Okay? In this case here, the probability of getting a sample of 11% if the true proportion is 20% is only a 1.2% chance. All right, well, probably not going to be true if there's only a 1.2% chance of something happening. So since there's only a 1.2% chance of something happening, probably have reason to doubt that this article's claim is true. We also have a random sample, so we know our sample's not biased. It should fall in the middle of the curve if the curve is true. We have the 10% condition, so we know that standard deviation's accurate. So then something's off. It's not our conditions, it's not our sample. It's probably where we centered our curve at. It was probably wrong. So that's our conclusion. If our p-value is greater than our significance level, we fail to reject our null hypothesis. We are never, ever, ever going to accept anything. I looked at some graphics to try to use in this slideshow, and the word accept popped up, and I just immediately said, nope, not doing it, because we do not accept the null. We just don't, we either have evidence against it, so we reject it, or we don't have enough evidence against it to reject it, so we're just going to kind of stand neutral on it, all right? We don't know that it's false, but we also don't know that it's true. We're just going to kind of stay put. Also, be sure to include context. Again, we mentioned that earlier, on your answer in reference to the alternate hypothesis. Your first sentence should be, since my p-value, 0.02 is less than 0.05, we reject our null hypothesis. And then since we rejected, we would say we have significant evidence that the true proportion of families in their 20s who have a garden is less than 20%, or whatever the context is of the problem based off of your alternate hypothesis. So if you reject your null, you have evidence of your alternate. If you fail to reject, you do not have evidence of your alternate. So those two statements kind of go hand in hand. Which one are you siding with? That's the one you have evidence for. All right, so the last little thing before we get into our example is the type 1 and 2 error. Okay, so type 1 and type 2. So as with anything dealing with probability or random chance, there's always a chance that you made an error, that just something, not necessarily that you made an error as the statistician, but that the findings you had by random chance were just incorrect. Okay, it doesn't necessarily mean, like I said, it doesn't mean you made a mathematical error. It doesn't mean your calculations were wrong, you didn't do the standard deviation wrong, nothing like that. It just means that we came to the wrong conclusion based off of our sample. All right, if I went and bought 10 lottery tickets and I won on one of them, All right, well, my sample kind of leads me to believe that there's a 10% chance of winning the lottery. We both know that is false, okay? So since that is false, that would be an error. Doesn't mean my sample was wrong, and it doesn't mean that the population mean of 0.00001 is wrong. It's just the two things didn't line up. Now, again, if I were to buy more and more lottery tickets, our increased sample size would, of course, bring us back within reason of how often we would win. The law of large numbers would come into play there. All right, so here are those two types of errors. So if you reject your null hypothesis and it was actually true, all right, so you said, hey, we got evidence here, and in reality it was true, that is a type 1 error. Okay? The one way that I remember that is that the decision you made was to reject. That is one word. Therefore, it is a type 1 error. All right, and the probability of making that error is sigma. That's your significance level. The area under that normal curve in your two tails is 5%. So there's a 5% chance that you could pull out that random weird sample, okay, with the population being true. So the probability of making that error is 5%. And then the type 2 error is when you failed to reject the null and that was incorrect, okay? So not rejected, we say failed to reject, okay? So failed to reject, if that were an error, that would be a type 2 error, meaning you said that the null was true and it actually wasn't, okay? You actually should have rejected it, but for some reason your sample did fall within that failed to reject region closer to the middle of our curve, so it wasn't enough evidence to reject. Okay. Another little acronym to remember those is hot hat. I found this online trying to come up with ways to learn that. So hot is when the null is true, but you rejected. Hat is when it's type 2 error, is when the ha is true, but you failed to reject. Okay. So you should have rejected, but you actually didn't. Okay. So hot hat is one way to look at that as well. Before we jump into our example, because I think we're good on time, are there any questions before we look at this example? You can put them in the chat. You can put them in the Q&A, either one. Just want to slow down for a minute before we go any further. All right, awesome. We're gonna hop on into this example here. All right, and this is from 2019, which is the last year we gave a real AP stat or normal AP stats exam. I don't want to say real. Okay, let's see. What was the hat example on the last slide? Oh, I know what you're talking about now. So a type 1 error, so hot hat, is when the ho is true, but you were wrong because it was an error, so you rejected. So you said that it was not true, and you rejected. Okay, that's a type 1 error. Hot comes first, then hat. So hot hat, the ho is true, and you rejected. Okay, and then hat is a type 2 error. That's the second one in the little mnemonic phrase there. Is when the ha is true, but you failed to reject. Okay, so in that case, if the ha is true, you should have rejected the ho, but you failed to reject it. Okay, and we'll look at more of that on the 5-hour cram. I'll definitely want to go back in a little bit more in depth on that, and I will make sure we find some examples that go more in depth on type 1 and 2 errors. I would suggest looking at the study guides from fiveable.me on type 1 and 2 errors and power. What's the probability of making a type 1 error, the probability of making a type 2 error, and how we can increase our power and decrease the odds of it making an error. And I'll say the most basic thing, if it asks how can you increase power, increase your sample size. Increasing sample size will bring up the power of your test, which lowers the probability of making a type 2 error. Type 1 error is just hinged on that alpha. It's hinged on that 0.05, the significance level. Okay? All right, so here is our example from 2019. Tumbleweed, commonly found in the western U.S., is the dried structure of certain plants that are blown by the wind. Kochia, a type of plant that turns into tumbleweed at the end of the summer, is a problem for farmers because it takes nutrients away from soil that would otherwise go to more beneficial plants. It sounds a lot like kudzu. If you live in the southeast, I live in Alabama. I'm sure you can tell by my accent. We have kudzu, and literally, like, you can watch it grow. Like, there are people like, yeah, you can literally sit and watch it for a day. If you watch it long enough, you'll see it grow. So what scientists are concerned about is that the kochia plants are more resistant to commonly used herbicide, which is glyphosate. In 2014, 19.7% of 61 randomly selected kochia plants were resistant to glyphosate. In 2017, 38.5% of 52 randomly selected plants were resistant. So you see an increase there from 19.7 to 38.5. Do the data give convincing statistical evidence at the level of 0.05, so our standard significance level, that there has been an increase in the proportion of plants that are resistant to glyphosate? Are tumbleweed plants or kochia more resistant to the weed killer? Okay, there's that key statement. All right, you see that last sentence? Immediately go to the 4 quadrants. We talked about that: state, plan, do, conclude. Some people do phantom or panic depending on if it's a confidence interval or hypothesis test. I don't like. I'm okay with cuss, although I think I'm going to change that next year to the socks. I think you guys convinced me earlier this cram season to do that, and I'm okay with SPDC. But I don't want much more than that. So that's your key statement. That should say, hey, this is a hypothesis test. I've got to do this. All right. So the first thing you want to do is you want to state. I'm going to clarify what tests I'm running. That kind of puts me on the right path. This one is, we're dealing with proportions. You see the word percent, and there's 2 of them. There's not like several percentages. And also there's 2. You have the proportion from 2014 and the proportion from 2017. Let me make this a little bit bigger for you. Okay. Hopefully that helps there. So a 2-prop z-test. All right, and then we got to state. I want to state what my parameters are. So notice how I did P 2014. The true proportion of probably coccia plants resistant to glyphosate in 2014. That makes sense. I didn't say P1 and 2. I used a subscript that was meaningful to the problem. And then, of course, its partner, P 2017, the true proportion of coccia plants resistant in 2017. So I have clarified what my 2 parameters are here. All right, and then the next thing I want to do for my hypothesis is my state is my null hypothesis. And when there's 2 proportions, the null hypothesis is that they're no different. All right, we're looking for data that it's higher in 2017, but we're looking at if there's nothing special going on here, everything is business as usual, then those 2 years are the same. Okay, some plants are just resistant to it. It's not changing. And then our null hypothesis here is that the proportion in 2014 is actually significantly lower in 2017. We can see that 19.7% is lower than 38.5. However, is it significantly lower? Or is it just because random chance we got a larger proportion in 2017. So this is your state portion. This should be the first quadrant. You've clarified what those two parameters mean. You've wrote them out into your null and your alternate hypothesis. Okay, so the next step we want to do is we want to plan. Quote the problem. All right, right here. I like underlining the problem or highlighting it as well because that's going to make sure you check that box. 61 randomly selected coccia plants. Check. 52 randomly selected coccia plants. Check. We're good. Both samples were randomly selected, so there should be no bias based off of my sampling. Okay. Independent. It is reasonable to believe that there are 610 coccia plants treated in 2014 and 520 plants treated in 2017. That makes total sense. Okay, both of those are reasonable statements to believe, especially if the coccia plant is like kudzu here in Alabama. There's thousands of them, and I'm sure farmers treat it like crazy. And then normal. Okay, this is that pooled proportion. Remember, two proportion when you assume that the two proportions are equal, which is what we did. We assumed that in our null hypothesis. We have to pool our proportions to check for normality. Okay, so first of all, in my calculator, I need to figure out what 19.7% is of 61. Okay, so 12.017, and then 38.5% of 52. All right, and I'm going to add those two together. Remember your reference page. Okay, remember we add them up. Here's our P combined. Okay. So 20.02 plus 12.017, which is 32.037, and then divide it by my total sample size, which is 52 plus 61. Okay, which is 28.3%. All right, so that's how I get my p hat combined. How many successes did I have in 2014? Add that with the successes from 2017, and then divide it by my total number of plants selected. Okay. All right. So you can see that over here. Our p hat is 0.2835. So then we take both sample sizes, 61 NP, N1 minus P, and then my N2, my second sample, times P, and then times the complement. All of those are greater than 10, so large counts is met. Okay, that was really, to me, this little bitty piece right here is the difference between someone making a 3 and a 4. It's that one little caveat that you just kind of forget about, and you just say, 19.7% of 61 is more than 10. 80.03 or 80.3% is more than 61, and so on for the other sample. But when you're doing a two prop, you have to combine those two. Okay, like I said, that's probably just the difference in a 3 and a 4 to me. You could probably make a 3 out of 4 on the free response, just doing the typical normal check. But we pool our proportions. We don't pool means, pool proportions. Okay, so that's your plan. In order to get full credit, that's how you would want to detail that out, and something similar to that. All right, then we want to do the test. So I'm going to go back to my calculator to do that for us. Okay. All right. So I'm going to go to Stat and go to Tests. We already said this was a two-prop z-test. So like these z-tests with nothing in front of them, or two sample z-tests, you don't ever use those, okay? So option 6, the number of successes we had I don't remember it, so I'm just going to find it again. So 0.197 times, that was 61 on that one. 61.385 times 52, and that was 52 total. And we are checking that the 2014 is less, so we got to define which way it is. And then we're going to calculate. Well, we have an error. Does anybody know? Let's just go back to the test. It'll say what I typed in. Option 6. Does anybody know what I did wrong? Well, clearly N1 is not 0. That's one thing I did wrong. That should be 61. All right. What else did I do wrong in my calculator? Anybody point out what I can adjust so that the calculator will work? Yes, not a whole X number. So those 12.017, all right, it's giving me a domain error. Just delete those, okay? Just make it 12. Round it down. You can round it up. Your answer is going to be about the same thing. All right, it will not, the test will not recognize a fraction or a decimal for the X value, okay? And then I'm going to hit calculate, and I get my z-score, negative 2.2, my p-value of 0.0135. Okay, and this is what it would look like on the normal curve. Centered at a z-score of 0 or centered at a difference in proportion of 0, and then my z-score of negative 2.2, that tail probability is really small, 0.013. All right, I know we're past 7 o'clock, so I'm going to wrap things up here. So then we got to conclude, since 0.01 for my p-value is less than 0.05 based off what I got in the calculator, we reject the null hypothesis. There is significant evidence at the 0.05 level that the coccinea plants are more resistant to glyphosate in 2017 than they were in 2014. Okay, that is the whole problem. That is all they gave you in 2019. Pretty much, I think each part was a point. Okay, getting the z-score and p-value was a point. The hypotheses were a point. Conclusion was a point. The conditions were a point. That's out of 4. Okay. Confidence intervals, typically there's not the hypothesis part, so there's a part B. But 2019, it was a hypothesis test based off of that last sentence, and SPDC did it. Okay. So I wanted to point out that error in the calculator because I had a lot of students that year who panicked because their calculator was giving them an error. Now what they did is they could see that they were different, so they just made up a number for p-value and then concluded correctly. They just said my p-value is 0.01 or 0.05 or 0.03 or 0.0001 or whatever, and then they just concluded based off of a made-up p-value. Don't stop if your calculator gives you an error. Make just kind of a judgment on, do those seem really different? In this case, they do. So just make up a p-value that's really low. You won't get the credit for the p-value, but you will get the credit for the conclusion. All right. So I made up a part B. What type of error would it be possible here based on your findings? And what is a consequence of making this error? So we rejected the null, so that is a type 1 error. A consequence of this would be that they decided to change the herbicides away from glyphosate to a more expensive one, when in reality the glyphosate was still working. So they're going to spend more money on updating their chemicals that they use, when in reality they didn't have to. The probability of a type 1 error is always your significance level. Type 1 error probability is easy. Okay? So that is the probability of a type 1 error. And again, our decision from before is that we rejected. So since our decision was that we rejected, that is a type 1 error based off the decision we made in that first part. Okay? And then the consequence, you're just putting in context there for your answer. And type 1 is always the significance level. Type 2 is the opposite of the power, which is a little bit different. All right, our non-negotiables. Be able to go through that full state, plan, do, conclude process for both one prop and two prop. Be able to determine which one it is based off of the context in the problem. Be able to decide which error concurs. Reject, type 1. You failed to reject, type 2. And they always like a consequence of that error just to get you thinking outside of just math in terms of the big picture of the problem. Be able to interpret the p-value. Remember, assuming the null is true, the probability of getting my sample is this. And the difference there, conclude the test. That's where you compare it to the significance level. Two different answers there. They get cross-pollinated a lot. But pay attention to the vocab. Is it asking you to interpret the p-value or conclude the test on the p-value? Be able to correctly identify the hypotheses on multiple choice. Always p, never p hat. And always equal in the null, some form of not equal in the ha, in the alternate. Either greater than, less than, or equal to. Never greater than or equal to. Never the underlined arrow. And be able to find the probability of type 1 error, that's significant, and the significance level, and understand how power is affected by type 2 errors. Okay, the probability of making a type 2 error is the complement of the power. If you want to increase the power, increase the sample size, and increasing the power lowers the probability of making a type 2 error. Okay, that's kind of our 5 non-negotiables for this week. We'll use those, especially number 5. I feel like we skimmed over it kind of quick. In the 5-hour cram, I'll make sure we find problems on those. I'm making mental notes of things that we didn't cover as deep as I would like to. Okie doke. All right. So that is it. Hop on over to the Fiveable, Fiveable Discord and the AP Stats channel for the after party, I guess you could say. And if you have any more questions, we'll be happy to answer those over there. We'll see you all, hopefully see you all Sunday at 1 p.m. Eastern time.